want to do one more explanation about specific heat. In the coffee cup calorimeter lab, we're actually measuring specific heat of metals, like this one for aluminum. Let me just review that really quickly. Okay, so what you did is you take a metal, okay? If you have, like I'm using these density cubes, okay? But you can also use like copper shot or aluminum shot or lead shot and put it in a test tube, but don't forget you need the mass, okay? So what you're going to do is you're going to have water inside this beaker that you heat, okay? You want to try to get it as close to 100 degrees Celsius boiling as possible. Also, you want the metal to be 100 degrees Celsius. So remember, you want to let it equilibrate, or actually, if you boil your metal, whether it's this cube, okay, or it's copper shot or a zinc shot, lead shot, whatever, do it for 10 minutes. Then you know the metal has the same temperature, and you can do several samples simultaneously. Okay, so this is what we're doing in the lab. Okay, we have our metal, okay, that we're boiling for 10 minutes. In our coffee cup, okay, we put 50. Doesn't matter how much you put in here. You put 50 milliliters inside the coffee cup calorimeter. Notice I just put and again, if you have a coffee lid cover, that's the best. But what you're doing then is you take this and immediately dump it inside the water, put the lid on, again, put the thermometer in, and you're going to watch to see what temperature it rises to. Okay, so you've boiled your metal 10 minutes, okay? You dump your metal, like in this case copper, inside, and you allow, again, you have a lid on it, hopefully you have one of those nice coffee lids, and you put the thermometer in and leave it in until the temperature stops. So, but we're trying to determine what's the specific heat of these metals, copper, or in this case, aluminum, all right? So we're using the same thing we did for our soda can calorimeter. We're using the idea of Q is heat. And Q is M times C times delta T. M times C times delta T. Mass times specific heat times the change in temperature. Because things aren't confusing enough, sometimes they use S for specific heat instead of C, okay? Just to keep things more confusing. Here's what we're saying. We're saying that all of the heat from this metal is transferred into the water inside our coffee cup calorimeter. That's exactly what we're saying here. We're saying that all the heat lost from the metal is gained by the water, specifically our aluminum or our copper. That metal, the heat from that metal, is then transferred over to the water inside our coffee cup calorimeter. That's what we're saying. So I have some sample data here. I have a mass of aluminum, mass of water. Let me remind you, we put 50 milliliters of water in. Water's density is 1 gram per milliliter, so 50 milliliters of water are 50 grams of water. Okay? You just weigh your aluminum for your mass. Now, what's the initial and final temperature of the calorimeter? Don't forget, after you put 50 mils in, what is the temperature immediately before you put your copper, your boiling hot copper, okay? What is it initially, and what is it after the metal raises the temperature, okay? Now the metal initially has been boiling, so we're going to presume it's pretty close to 100. Don't assume just because it's boiling that temperature is 100. Be sure to check it, because if you're using tap water, the minerals in that, it may not reach 100. Might even be a little more than 100 even. Okay, now, so we have our initial temperature of the calorimeter, that's the water inside that coffee cup calorimeter, and the final. The metal initially is 100, and the final would be the same temperature inside the calorimeter. The metal that was 100 is now going to be the same temperature as the water inside the calorimeter. Now, So let me show you how I calculated this. This is the accepted value. When we say literature, we mean this is what we accept to be the value for the specific heat for the metal aluminum. Now, so here's the premise, that all the heat from the water is transferred to, all the heat from the metal is transferred to the water. So let's calculate it. So what is the Q, or the heat, for water? Okay. So we have here, we get 50 grams, 50 milliliters is 50 grams of water. Okay. Now, when we did the soda can, we said the specific heat of water is 1. It is 1 calorie per gram degree Celsius. But it's also 4.182 joules per gram degree Celsius. So we're using that, and the change, what we have here too, is what's the change in temperature? It is 12.9 degrees. So when we multiply 50 times 4.182 times 12.9, we're going to get 2697.39. Now, aluminum, what we're really trying to figure out here is what is the specific heat here for aluminum? What do we calculate it to be? So we have, though, the mass of aluminum, okay, and we know that the final temperature is 32.9, the initial was 100, so that is negative, so we have here, when we have this is going to be negative 67.1, when we take 46.31 times x times 67.1, we're going to get negative 3107.4 x, okay? So all the heat from the metal is transferred to the water inside the calorimeter. So this value is negative 3107.4, okay? When we solve for x, x then is 0.87 joules. Now, what's our percent error? We can even calculate that because we have the accepted value. Remember, when you do percent error, we take the absolute value of the accepted minus the experimental divided by the accepted, and we calculate it to be about 2.22% error. So these are a little more complicated because you have to calculate both the Q, or heat, for the water and the Q for the aluminum. And then what you're doing is backing into what is the specific heat that we calculate experimentally for the metal. That's it.